Okay, related rates, we're going to acknowledge the fact that as time goes on, more variables than just one are changing. So we'll need to know the relationship between how the different variables change. For example, if we're pumping air into a balloon, both the volume of the balloon and the radius of the balloon are increasing. And their rates of increase are related to one another because the volume of a balloon is dependent upon its radius, but it's way easier to measure the amount of air going into the balloon than it is to try to measure the radius from the center of the balloon. So the chain rule is going to help us with this. And we'll start with that exact example. So air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. So I'm going to write that down and give it a name. That is change in volume with respect to time is equal to 100 cubic centimeters per second. Now, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So my question is, what is dr dt when diameter, so d equals 50 centimeters? That's the question I'm trying to answer. So, I happen to know the volume of a sphere. The volume of a sphere is equal to 4/3 pi r cubed. So I can differentiate that using the chain rule, implicit differentiation. So, the derivative of v with respect to t has to be equal to 3 falls down, 3 times 4/3 gives me 4 pi r squared times dr dt. Well, I know what dv dt is. I'd like to know what dr dt is. This is my goal. And I have something I can plug in for here because I want to know how it's changing when d equals 50, which would be r equals 25. So on the left-hand side, I have 100 cubic centimeters per second. Has to be equal to 4 pi times 25 centimeters squared times dr dt. So now I can divide both sides by all of this stuff, and I think I'll go ahead and square 25, 625. So I have, oh, and let's go ahead and multiply it by 4, 2500. So that gives me 100 centimeters cubed per second over 2500 pi, and I have centimeters times centimeters, so that's just centimeters squared is equal to dr dt. And now I can simplify a bit, and I would have 1 over 25 pi, and let's see what my units should be. I've got cubic centimeters per second divided by centimeters squared, so that just leaves me with centimeters per second is equal to dr dt. And if you keep your units along, you'll know that you've ended up with the right units because radius changes as centimeters per second. It's just a length measurement. And then if we were going to write about what was happening, we would say the radius is increasing at a rate, and I have no idea what 1/25 pi is, so I'm going to do 1/25 pi, and you notice I use my fraction bar, so I don't do 1/25 pi, because that would multiply pi times 1/25, and I get 0.0, I'll give it 4 decimal places just because it's a nice stopping point, centimeters per second. Now I just kind of approached this problem and started working it, but there is a very structured way you can go about these problems. First thing you do is identify 3 things. This is your setup. For your setup, you need a know, a need, and a when. So this was my know. I know that dV dt is equal to 100 cubic centimeters. My need was dr dt. And my when was the diameter equals 50 centimeters. So if you can go through all of these words and just pick out these important things, you're well on your way. Now, once you get the setup done, you're going to do 3 other things. Now, this tells you that you do need to add in some variables. There's our know, our need, and our when. After you set up, in order to solve it, you relate, differentiate, evaluate. Relate is easy. You just have to figure out which formula you're going to use. In this one, it was volume. Differentiate. Again, that's easy. You know how to differentiate stuff. Evaluate is the tricky one. That's where your knows and your whens come back and you plug them in and solve for what you need. Differentiate, evaluate, and there we go. So here's our problem-solving strategy. Read it carefully. If you can draw a picture, draw a picture. Now, a picture of a balloon that I draw would not be helpful at all, so I didn't even try to draw that. Write down your know, need, when, and introduce your notation. Assign symbols to all quantities that are changing over time. And then you relate, differentiate, evaluate. And you got it. Let's practice another one, and it happens to be another balloon problem. I went ahead and made myself a little chart, know, need, and when, to remind myself what I'm looking for. A balloon is being inflated at a rate of 17 cubic meters per second. If it maintains its perfectly spherical shape as it is inflated, how fast is its radius changing when the volume is 27 pi cubic meters? Okay. My know is 17 cubic meters per second. Now another little clue that that's the change in volume is that it's being measured in cubic meters, and volume is measured in cubic meters. So dV dt is 17 cubic meters per second. Units are important. How fast is its radius changing? So my need is dr dt. When volume is 27 pi cubic meters. So volume equals 27 pi cubic meters. Alrighty, we can do this. Know, need, when. Setup complete. Now we're ready to start relate, differentiate, evaluate. So, relate, same relation as example 1. Volume is 4/3 pi r cubed. Differentiate. You know I'm going to get tired of writing this down. dv is 3 falls down, 4 pi r squared, dr dt, because they're both changing over time. And now we have to evaluate. Well, 17 cubic meters is true all the time. I want to know what R is when volume is equal to 27 pi cubic meters. So 27 pi is equal to, and volume is 4/3 pi r cubed. So 23 times 27 gives me 81 pi over 4 pi is equal to r cubed. So r is equal to the cube root of 81 over 4. You could write it as 3 times the cube root of 3 if you wanted to, but that's really not that much prettier than that answer. So now we're ready to evaluate. dv dt we know is 17 is equal to 4 pi times the cube root of 81 over 4 squared dr dt. So for an exact answer, it would be not that pretty. dr dt is equal to 17 over 4 pi times the cube root of 81 over 4, and this was cubic centimeters per second. This is centimeters squared, so I end up with exactly the units I want, which is centimeters per second. And I can plug all that into my calculator and get a decimal answer. Note that I did go back and add my squared that I had left off there. And when I put it into my calculator, I just put 81 over 4 to the 2/3 power, same thing as the cube root squared. It's just a whole lot easier to plug that into my calculator. Oh, example 1 required us to know a geometry formula, and you are going to need to memorize the volume of a sphere, the volume of a cone, and the volume of a cylinder. So those are things that you need to know. This next one has to do with a right triangle, and this one's going to rely upon the Pythagorean theorem. We have a ladder that is 10 feet long, rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 4 feet per second, how fast is the ladder, the top of the ladder, sliding down the wall when the bottom is 6 feet from the wall? So first thing I'm going to do before I even start knowing, needing, or winning is to draw a picture. If you can draw a triangle, you can draw these pictures. They don't have to be perfect. Now, the ladder is not going to change. It's always going to be 10 feet long. So I could go ahead and label that with 10. I'm a big fan of naming horizontal things as x's and vertical things as y's. If you wanted to call it something else, you could. That would be okay. So now I have variables for the different things. I can write down my no, my need, and my when. The bottom of the ladder slides away from the wall at a rate of 4 feet per second. So it's going this way. That means x is getting bigger. So I know that dx dt is equal to 4 feet per second. Things moving fast. Let's look at need. How fast is the top of the ladder? Oh, well, here's the top of the ladder, so it's asking for dy dt. When the bottom of the ladder, that's x, is 6 feet from the wall. Setup complete. We're ready to complete the problem. So let's relate. This is a right triangle. X squared plus y squared equals 10 squared. So I'll label it relate. Now let's differentiate. 2x dx dt plus 2y dy dt is equal to the derivative of a constant is 0. So now I know what dx dt is, and I want to know the answer to this problem when x is equal to 6. So I'm going to draw what I call a when triangle. Hypotenuse, 10 all the time. My when x is equal to 6, I need to know what y is. So y squared plus 6 squared equals 10 squared. Y squared equals 100 minus 36, which is 64. So y is equal to 8. Now I know if you were solving an algebra problem, y squared equals 64, then y equals plus or minus 8, but you're not going to have a negative y. The top of this ladder has not buried itself into the ground. We're only interested in the positive solution in this case. So now I have a y. Now I'm looking up here and I see I have 2 times x, 2 times y. I can divide everything here by 2, and those cancel. So I really just have x dx dt plus y dy dt is equal to 0. So 6 times 4 feet per second. And let's put the units in just to be sure that we have the right units for our answer. So x is 6 feet times 4 feet per second plus y is 8 feet dy dt is equal to 0. So 8 feet is equal to negative 24 square feet per second. 8 feet times dy dt. I really want dy dt all alone, so I divide both sides by 8 feet divided by 8 feet. So dy dt is negative 3. I have square feet on top, feet on the bottom, feet per second. And since y is just how far the distance this ladder is up the wall, that's an appropriate units. We did everything right. Kind of a good error checking device. And we have all the pretty answers here. There's my wind triangle. And we're sliding down the wall at a rate of 3 feet per second. When you write your sentence, you can say it's sliding down the wall, and you don't have to have the minus there. Practice number 2 is another ladder problem. We have a 15-foot ladder resting against a wall. The bottom is initially 10 feet from the wall and is being pushed towards the wall at a rate of 1/4 feet per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? So in example 2, the ladder was moving away from the wall. This time the ladder is moving towards the wall, but we still draw a triangle. The ladder is still, the hypotenuse and the length of the ladder still does not change. I'm still going to call this guy X and this guy Y because it makes me happy to be consistent. Make sure you can see that 1 there. What do I know? I know that it's being pushed towards the wall, so this way. X is getting smaller, so dx dt is negative 1/4 foot per second. I need how fast the top is moving up the wall, dy dt. And this one's different because it doesn't give me a length for my wind. It gives me t equals 12 seconds. So, let's go ahead and relate. X squared plus y squared is 15 squared. Differentiate. 2x dx dt plus 2y dy dt is 0. So x dx dt, you don't have to get rid of the 2's, but I usually do just to make it simpler. Now, evaluate. I know my win is 12 seconds. I need to know what is x after 12 seconds. I can write myself a little function for that. X after t seconds is equal to, it starts out 10 feet from the wall. Every second, it's getting 1/4 of a foot closer to the wall. Yeah, that's what the derivative of that function is, negative 1/4. Oh, cool. That's right. So, x after 6 seconds is equal to 10 minus 1/4 times 6, which is 10 minus 6 over 4, which is 10 minus 3 halves, which is 20 over 2, minus 3 over 2 is 17 over 2. I made it 6 seconds instead of 12. That was silly. Let me fix that. Got to read it correctly. I want x after 12 seconds, not 6 seconds. The good news is that makes it 10 minus 1/4 of 12 is 3, which is 7, so no stinky fractions. So now I still need a Venn triangle, because I know what x is, I got to use that to figure out what y is. So another triangle, x is 7, z, or hypotenuse, is 15, so y squared plus 7 squared is 15 squared. So y squared is 15 squared, 25 minus 49. So y is the square root of 176. So x dx dt, that would be 7 times negative 1/4 plus y square root of 176 dy dt equals 0. So dy dt equals, well, we add 7 over 4 to each side, divided by the square root of 176. Plugging that in my calculator, I'll start with a fraction bar. I put 7 divided by 4 on top of the fraction bar. You could have put 7 over 4 times square root of 176, but you end up with about 0.13. So the top of the ladder is sliding down the wall. Actually, is sliding up the wall, because that's getting bigger, is sliding up the wall at a rate of 0.139132. We'll round it to 2 feet per second. Okay, we'll stop here. Maybe practice some with Pythagorean theorem and with just geometric formulas in them, and then we'll learn some more.